And thanks very much for Bernardo for this fantastic meeting here. I am very, very honored to be here. And I would like to begin this talk dedicating this talk to a very good friend of mine, Jose Fernando Chepe Escobar. And if you would allow me, I would like to read what's in there. So, born in Manizales on December 20th, 1954, Chepe studied mathematics at the Universidad del Valle, got his master's degree from IMPA and his PhD from the University of California, Berkeley, in 1986. He taught at many leading universities and academic centers such as Chicago, Indiana, and Cornell. He also held many visiting positions such as in IMPA, the Curran Institute of Mathematical Sciences, the Mittag-Leffler Institute, the University of Warwick, and the IHES. In 1994, he joined the Department of Mathematics at Cornell, where he had many PhD students, especially Latin Americans, including Fernando Coda Marquez, one of the invited speakers in this Congress, who unfortunately had to cancel his participation. On January 3rd, 2004, Chepe was on sabbatical at the Universidad del Valle, and Chepe passed away after a long illness. Among the awards he received for his work are the Alfred Sloan Fellowship and the Presidential Faculty Fellowship received at the White House directly from the hands of the President of the United States. So Chepe was a very, very good friend, and I would like to show you this picture here, which was taken during a Cinco de Mayo celebration at the Greek Theater in Berkeley, which is probably where I started to learn the little Spanish that I can speak. And I also started to learn a bit of salsa dancing with Chepe. And Chepe was a very good friend who we all miss very much. Okay, so to mathematics now. My talk is Partial Actions in the Banach-Tarski Paradox, and it's based on this paper with this joint work with Pereara from the University of Barcelona. Okay, so let me begin by describing the Banach-Tarski Paradox, which was proved in 1924. So we let BR be the solid ball of radius r in R3. So what they proved is that there is a partition of the ball in finitely many sets. And there are also linear transformations in SO3, that means rigid linear transformations, such that if you take the first n of them, first n of the sets, you move them under these transformations, you get another copy of BR, and the same thing happens with the rest of them. So this is to say that one ball may be broken into finitely many pieces, which in turn may be used to form two identical balls. This is called a paradox because it's very counterintuitive, but it's not a paradox, it's a theorem. It's been proved. But it has some interesting consequences. So here is a picture of Banach and Tarski, the people responsible for proving this result. And so here's a consequence. As a consequence, I'm going to prove to you that 4/3 of pi r cubed is equal to 8/3 of pi r cubed. I'm going to prove that to you. Okay? Do you believe that? So here's a proof. The proof is that the volume of the ball is equal to that. But the volume of the ball is equal to twice the volume of the ball, which is that much. So the precise proof is here. The volume of the ball is the volume, so this is the decomposition of the ball that I just showed to you. Now the volume of this disjoint union is the sum of the volumes. Now the volume is invariant under translation, so you can stick in the transformations in here. Now you put this together, so the sum of the volumes is the volume of the union, and the volume of the union is the volume of the ball. So the volume of the ball is equal to twice the volume of the ball. So if there is anyone from the press around here, please don't go away yet, because I'm not done. So there's something wrong. So what's wrong? Most people would say it's the Banach-Tarski paradox. This is impossible. But the point is that the Banach-Tarski paradox is correct. What is incorrect is the computations that we're doing here, especially the properties of the volume that we're using. So which properties are we using? The volume of the disjoint union is the sum of the volume. That's called additivity. And the volume of a transformation is the same of the volume provided T is a rigid transformation. So the trouble here is that there is no such volume function defined for all subsets in R3. So the difficulty to understand the Banach-Tarski paradox is that these pieces that this ball is broken into are very weird sets. You in fact need the axiom of choice to prove that there exists. So the main consequence of the Banach-Tarski paradox is that we must give up attempting to define the volume for all subsets of the space, and instead we need to look only at measurable subsets. So this is the content of measure theory, which people learn at the university. But I'm not going to take that path. I'm going to insist in trying to measure the volume of all subsets in the following slightly more general situation. So here, let's suppose that X is a given set, G is a group, and we are giving a group action of G on X. So what do I mean by that? I mean that for every group element in G, I have a bijective function on my set X, such that theta 1 is the identity map, and the maps composed according to the group law. Okay? So in the previous case, the case of the Banach-Tarski paradox, the space, the set was R3, the group was SO3, and the action of a T, an element T on X, is simply applying the linear transformation to X. Okay? So the question, the problem that we're going to pose ourselves is this. Let's try to find some function, which we might as well call volume, defined on all subsets of X, taking extended real values, and we want that function to be additive and also invariant under group action. Okay? So there is an example. An example is the identically zero function. Another example is the identically infinite function, but things get more interesting if we want the volume of a certain set, which maybe we prescribe to be a positive finite number. So in order to study this problem, let me introduce a concept which is very important called the type semigroup. So the type semigroup is a commutative semigroup denoted SXG, which is defined via generators and relations. So for every subset of X, we have one generator of this group, so this group has many, many, many generators. Then, whenever you have two disjoint subsets, we introduce a relation that says that the generator corresponding to the union should be the sum of the corresponding generators. So this here is the sum in this new semigroup that we are building, okay? Then, for every element in the group, we want that the generator corresponding to the transform of E is equal to E. So elements in the semigroup, every time you have a commutative semigroup with a set of generators, the elements are necessarily of the form a linear combination of the generators with natural numbers as coefficients. Okay? So these are the elements. So if we have two subsets in X, how can we decide if the two subsets are equal? For example, one ball as opposed to two balls. Well, the only way is to break one set as a disjoint union, then move the sets according to group elements and form the other set. So if that's the case, then the class of E, that's by one of the relations, is the sum of the class of the ENs. By the other relation, you can stick in the group elements in here, and you get F. Okay? So this is essentially when two elements in the semigroup are equal. So I challenge you to tell me, are these equal? How about that? Are these equal? So have anyone here seen these pieces over here? Whoops. So you can switch. You can switch from the square to this funny picture here by breaking it like that. So these are the 7 pieces that form a very ancient Chinese game called Tangram. And I have some examples of Tangram here. So all of these are the same. Okay? So this is an exercise for you to prove that they're all equal to each other by breaking and then putting together. But, well, I guess you have had a very long week, so I'm going to help you doing this. So here we are. So all of these are the same according to this point of view. Okay. So let's, based on these definitions, let's view the Banach-Tarski paradoxes slightly differently. What it says is that in the type semigroup of the action of SO3 on R3, you have the 2 times the ball is equal to the ball. Now, in any semigroup, there's an order relation. You can say that on a semigroup, x is less than y if there is an element z such that x plus z is equal to y, right? So let's give a definition and let's say that a set E is paradoxical if 2 times E is less than or equal to E. In the case of the Banach-Tarski paradox, you actually have equal here. So after Tarski and Banach found this paradox, Tarski went on to try to understand more general situations, and Tarski proved this theorem. So given a set E, in this general situation of a group acting on a set, this set, the class of E is not paradoxical, meaning that this is not the case, if and only if there exists an additive G-invariant volume function which assigns volume 1 to E. Okay? Now, it's elementary to show that 2 implies 1. Essentially, that stupid computation that I did that was 4/3 of pi r cubed is essentially a proof that if you have a volume function, the set cannot be paradoxical. Okay. Now, let me give you a definition, which is going to be very important for what we do from now on, which is a definition of a partial action of a group on a set. Well, the idea is to generalize the notion of a group action on a set. And we have a group G, a set X, and I have a collection of subsets indexed by the group elements, those XGs. And for every group element, I have a map from XG inverse to XG. Okay? So if all of the XGs are equal to X, then we're talking about a group action. Now here, we want theta 1 to be the identity. So in particular, we want X1 to be X. And then the group law, which in the case of a group action says that theta G composed with theta H should be equal to theta GH. Here we want an inclusion. What do I mean by an inclusion of maps? Well, a map is containing another one when the other one restricted to the domain of the first map is the... So by this I say that this map extends that composition. But once we are playing with partially defined maps, we have to worry about the meaning of a composition of maps. Okay? So this diagram here is supposed to explain what is the partially defined composition. So let's look at here. So here I depicted the map theta H, which goes from XH inverse to XH. I depicted the map theta G, which goes from XG inverse to XG. And we want to compose. So we start with a point here. We go via theta H, and then we want to go forward. Now, of course, the point might, when we start here, applying theta H might land here, so it's impossible to compute theta G. Sometimes it is, sometimes it's not. So where can we do this? So look at the intersection. xh intersection xg inverse, bring it back under theta h. So these are the set of points such that if you go via theta h, you land inside the domain of theta g. So for those points, this is the domain of the composition, and of course the map is defined as obviously as you can think of. So this is a definition of a partial group action. Okay. Oops, where am I? Okay. Now the interesting thing is that everything I told you, or almost everything I told you about the Banach-Tarski paradox and the Tarski's theorem, still holds when you pass from group actions to partial group actions. So you can still talk about invariant volume functions in the type semigroup. So what's a volume function? This is a function defined on all subsets. And now we want the invariance to satisfy this property here only when theta g is defined on E, and that means when E is contained in the domain of theta g. Also, when you define the type semigroup by this relation, we only use E's when E is contained in here. And what's interesting is that Tarski's theorem, as I said, holds exactly as stated, in the sense that there exists a volume function even only if E is not paradoxical. Okay. Now let me change the paradigm. Let me change the problem. Before we were talking about group actions on sets, and now I want to talk about group actions on totally disconnected topological spaces. Okay? So a totally disconnected space is a topological space, or actually a locally compact, totally disconnected space, is a topological space which admits a basis formed by Klopen subsets. So one of the main examples is the Cantor set. The Cantor set, you know how to do it. You take the middle third away, and then you keep doing that, and the intersection is the Cantor set. So this Cantor set appears in many, many places in mathematics. It has already been mentioned here in this conference many times. And it shows up in dynamical systems, number theory, p-adic integers, and in many other situations in math. Even the rings of Saturn look like the Cantor set. No? That you take pieces away. Okay, so from now on, X will be a compact, totally disconnected topological space. And now we are looking at a partial action of a given group G on X. And we assume that all of those XGs, the domains and ranges, they're all Klopen, and that the maps are continuous. So this is the main change in our point of view, that we're no longer going to try to measure every set. We only want to define the volume for Klopen subsets. So let's introduce this letter K here to mean the collection of all Klopen subsets. And we're looking for an additive G-invariant function defined only on Klopen sets. So remember, before we had the type semigroup SXG. Now I'm talking about the type semigroup SXGK. By that I mean that I am restricting myself only to Klopen subsets. Okay? So it's the main definition, except that we do it on Klopen subsets. So the question is Tarski's theorem still true in that context? So one direction is obvious. If there exists a volume function defined only on Klopen subsets, then E is not paradoxical by trivial reasons. So the question, is the other direction true? So this is the other direction. Given that a set is not paradoxical, can you find a measure? That's the difficult part in Tarski's theorem. And it's also the crucial point here, because this is false. So if you want to take home one lesson from my talk, that's the lesson. If you move from all subsets to Klopen subsets, then Tarski's theorem is no longer true. And my main intent here is to show you an example. So I want to describe an example in which a certain Klopen set is not paradoxical, meaning that 2 times E is not less than or equal to E, But still there is no volume function satisfying this property. So that implication here is false for this set. Why would it be? What's the problem? The problem is that the set is going to be paradoxical in a non-conventional sense. It's a different sense from what Tarski had in mind. And the reason is that 2 times E is going to be 3 times E. But E is not going to be bigger than 2 times E. So if you have a volume function, then 2 times the volume of E is had to be equal to 3 times the volume of E, so that forces the volume to be either 0 or infinite. So this is our goal. Find an example of a group acting on a Cantor set such that for a certain set E, 2 times E is 3 times E, but this is not true. So this will block the chance of generalizing Tarski's theorem. So in order for me to give you this example, I have to introduce a notion of an NM dynamical system, or in this case, a dynamical system of type 2, 3. So what is it? So what I have in mind is a topological space X, which has a partition in 2 subsets, E and F, both of which are compact. So the space is depicted here. This is one part, and this is the other part. Furthermore, the part F has 2 different partitions. One partition in 3 subsets H's, which you should think of the horizontal slices, and also there are 2 vertical subsets. So I want those to be all Klopen subsets. So this is, you see that this has to be highly disconnected. Now, also I want maps from E, so the little hi is a map from E onto the horizontal slice, and H1 should be a homeomorphism onto H1, and H2 and H3 so on, and likewise I want homeomorphism from E to the vertical columns. Okay, so HIs and VJs are homeomorphism. So this is what a 2-3 dynamical system is. You may think of, do you have examples of a 2-3 dynamical system in mind? It's not so hard. I mean, if you play with, the Cantor set is a set in which half of it is equal to itself, right? And so you can take, maybe you split it in many times. I mean, there are ways to do it. It's not a very difficult thing. But let me skip the sentence here and go straight here. There are many such systems, but there is one system which is kind of the biggest one, which is the mother of all 2-3 dynamical systems. And I do not want to go into the definition of that system, but it exists. And this is a universal system, and so from now on, we'll look at the universal system. So the interesting thing is that H1, H2, H3, V1, and V2, they are already partially defined homeomorphisms, okay? So it looks like there's a partial group action behind the scenes, and in fact there is. You take, how many are there? There are 5 maps, okay? So take the free group on 5 generators. And so take the generators of the free group to act on our space according to H1, H2, H3, V1, and V2, and then the other group elements you have to iterate. There's a standard way to do this. Okay, in this case, in this example, 3 times E, let's now think of the type semi-group of this dynamical system. 3 times E is equal to E plus E plus E, but then I can stick in H1, H2, and H3, right? And the union of this is F, and in the similar way you get V1 of E plus V2 of E, which is 2 times E. So 3 times E is equal to 2 times E, and if we are worried about this, let me back up a little bit. This is our goal, to find an E satisfying this, then this is, we have already done it, right? 2 times E is equal to 3 times E. The hard part is proving that 2 times E is not smaller than E. I have plenty of time still, right? Like 20 minutes, good. Okay, so how do we do this? So proving that 2 times E is less than E involves a lot of machinery, involves cross-product algebras, K-theory, separated graphs, and some monoid theory. And a large part of this machinery is where Pereira, my co-author, is a specialist. He's been working on this kind of stuff for a long time. So how do we go about, I mean, of course I'm not going to try to prove anything here. I just wanted to show you the kind of techniques that are involved. So let's start by taking any field, K. You could take the complex numbers, the real numbers. And let's look, so this X here is our space where our 2-3 dynamical system acts, okay? And so let's begin by looking at all functions from X to K which are locally constant, okay? On a totally disconnected set, you have plenty locally constant functions. For example, these E and F are clopin subsets in our space. So 1E and 1F, they are elements of this algebra L of X. And because F is broken as the union of the H's, you have this equality here in this algebra of functions, and so on. Now, we have to take a very difficult step, which is building the cross-product algebra. So in order to give you a precise definition, that would take a long time, but I think I can give you a flavor of what it is. So the cross-product algebra includes L of X, but then you throw in more elements to this algebra, and you throw in a new element called UG for every element in the free group, okay? And you want this element UG to implement the partial action in the following sense. If you have any function f in L of X, now that the algebra is now bigger, you can multiply your functions by this group elements, okay? And I want this sort of conjugation here to mimic the dynamic. By that I mean that every group element G is associated to a partial homeomorphism, so I may compose my function with this partial homeomorphism. So this is the algebraic rule here. So roughly speaking, the dynamics of that system is codified in the algebraic structure of this algebra. I wonder if there's any questions so far on this. This is, I mean, one point of view is that in an algebra, the nicest automorphisms are the inner automorphisms, right? If you have an algebra, you like inner automorphisms. But sometimes you have an automorphism which is not inner. So what do you do? Well, you may force an automorphism to become inner by adjoining an element in the algebra to do the inner thing for you. So what we're doing here is essentially the same, except that these are not automorphisms, but those are partial automorphisms. Okay. Next, we must study some K-theory inside this algebra. So the idea is to study the structure of the set of idempotent elements in this algebra. And in fact, we have to study not only idempotence in the algebra, but idempotence in the matrix algebras for all sizes of matrices, okay? So, in fact, in any algebra, we can play the following game, which in a sense is similar to building the type semigroup. Maybe I should say that clopin sets correspond to every clopin set. If you look at the characteristic of the clopin set, that's a function that's idempotent, right? So in a sense, idempotent elements should be thought of as clopin sets. So we begin by saying that two idempotent n by n matrices are equivalent. If you have ever taken a class in linear algebra, you know what equivalent matrices are. If there is an invertible matrix U that conjugates one onto the other. Okay? So this is the notion of equivalence of idempotence. Now, this idempotence, they have to be the same size. But in our relation, we are going to allow idempotents of different sizes to be equivalent. So the standard equivalence is that we take an idempotent F of size n plus n, then we stick in zeros to make this matrix bigger, and of course, this is now a new idempotent matrix, and we are going to declare that F is equivalent to this idempotent. Okay? So you define an equivalence relation by this elementary notions, and so we can form a commutative semigroup consisting of all of the equivalent classes of idempotent matrices, and here n, we're looking at all n's, under the addition operation that we form like this. So the sum of two elements in this group is the direct sum of the idempotent matrices. So if I started with instead of this funny algebra here, if I started, say, with the real numbers, what would be this semigroup? This is a question for students. So what is? What is the main quantity that is looking at you when you have a real idempotent matrix, which is invariant under this two equivalence relations? So it's the rank, right? Two matrices which are equivalent in that sense, if they have to be have the same rank, and of course the rank of F is the same rank as this matrix, so the rank is the essential quantity behind here. So this type semigroup, the semigroup here is simply the semigroup of all possible ranks, namely the natural numbers. Okay, so the notation for the semigroup is usually a curly V of the algebra over here. Okay, so let's now define, so we have now two semigroups, two very important semigroups. The first one is the type semigroup corresponding to the action of the free group on our universal 2-3 dynamical system. And the other one is the type semigroup corresponding, the semigroup I just defined to you here for this algebra. So we may define a homomorphism of semigroups from this type semigroup to this semigroup as follows. So this guy is generated by Clopin sets. So take a Clopin set and look at the class of the Clopin set and send that to the characteristic function on this Clopin set. This, as I told you, is an idempotent element, and so it has a class in here. So over here, we had our set E, which satisfied 2 times E equal to 3 times E. So if given that phi is a homomorphism of semigroup, that same condition is going to hold over here in this other semigroup. Now, this thing gets extremely technical, and I really cannot go into the details, but what you can do is show that this map phi is an isomorphism. It's a semigroup isomorphism. This is a very heavy machinery. And so since it's an isomorphism, all of the questions that we ask here, we can ask here. And there's another very heavy-duty, result saying that in this semigroup, 2 times E is not smaller than 1E. So essentially, the conditions on the set we want hold on this side, so they have to hold on this side. So there is no invariant volume function on the sets satisfying this, but the obstruction is not that E is paradoxical, because it's not paradoxical in Tarski's sense. The obstruction is that 2 times E is equal to 3 times E. But you may not like this very much, because I'm giving an example of a partial action in which Tarski's theorem is not valid. So we might wonder whether it's possible to have a global action. So I have to boost this up to a global action. Okay, so as I say, so far we have obtained an example of a partial action, but we may also create a global action. You know, in our community of partial action people, that may be a little bold to say, but for us, an action is really a partial action. There is a very specific kind of action that some other people look at, and so we have a special name for them, global actions, right? So by a global action, I mean a usual action as opposed to partial action. Sorry about that. So where was I? Okay, so how do we build a global action from a partial action? So this is theory of Fernando Abadiz of globalization, which is a very nice theory. I like it very much. In fact, Fernando developed this in Florianopolis when he was finishing his PhD. Fernando is an incredibly independent mathematician. I mean, we would talk occasionally, and he would every time bring all those interesting ideas. So let's begin with a global action. So this is eta is an action as you are used to. Okay. So suppose. So this action eta is acting on the set x tilde. Okay, it's important to notice that. Now suppose we have a subset x inside of x tilde, and we want to restrict our action to x. Everybody would say, well, you can only do that if x is invariant. But suppose x is not invariant. Is it still possible to restrict an action to a non-invariant set? Okay, so this is a picture of x tilde. This is a picture of x, and in this picture, the image of x under eta sub g is this other circle here, so it's not the same as x. So this is a picture of an action which has a non-invariant set. So what do? Well, you want to map things inside of x to things which are also inside of x. So you introduce this notation. X sub g is the intersection of x with its image. So this is the definition of xg over here. Now, it's an interesting thing that if you take g inverse over here, so you take x intersection eta g inverse of x, so this is what we're going to call x sub g inverse. Okay? If you apply eta g here, this x goes to eta g of x, and where does eta g inverse of x go? Well, eta g inverse under g goes to x itself. So eta g maps xg inverse to xg, and therefore defines a partially defined map on x. So this is the crucial idea behind the notion of partial actions. A partial action, in a sense, is what you get if you want to restrict a global action to a subset which is not invariant. Okay. Now, given a partial action, so in the last slide, I show you how to go from a global action to a partial action. Now let's go the other way. So given a partial action of g on x, we want to ask if there exists a global action such that the restriction to the subset x is the given partial action. Okay? This is called globalization. So the answer to this question is yes, and there is a canonical way to do that. From a partial action, there's a canonical way to get a global action. This process, this globalization process, is slightly tricky. It works well here if we're talking about clopin sets. But if you're a partial action, see, one example of a partial action, I mean, one of the most well-known examples of partial actions, which I bet every one of you know, is the example of an incomplete flow on a manifold, right? If you have a vector field on a non-compact manifold, it's often the case that the solutions cannot be defined for all time, right? So if you define the flow only for the elements that allow an evolution of that long, you get a partial action. So it's an interesting question. Is this partial action globalizable? So the question is that if you take global actions on non-compact and non-totally disconnected spaces, this Fernando's result, which is still true, that every partial action has a globalization, will lead you to a non-Hausdorff space. So in general, this process is complicated. But here, it works quite well because the space is totally disconnected. So if we take the globalization of the above 2-3 dynamical system, we get a space X tilde, which is somewhat concrete to be defined. And one of the theorems of Fernando, which is in fact stated in the language of Morita equivalence, says that the two type semigroups are isomorphic. So we had a type semigroup coming from a partial action, and we reconstruct the same type semigroup at this time coming from a global action. So if we have this type of a non-standard paradoxicality over here, then the same thing holds here. So in other words, there exists a Clopen subset in X tilde such that 2 times E is 3 times E, but it's not paradoxical. Therefore, there is no additive invariant volume function satisfying this condition. So Tarski's theorem do not generalize to Clopen sets. That's unfortunate. And these are the main references. This is Fernando Abadi's thesis over here, enveloping actions. In fact, the terminology nowadays is globalization, but Fernando used to say enveloping, and this is the other paper that I showed you at the beginning. So thank you very much for your attention.